Okay, let's begin. So we have started looking at predicate logic, which is also known as first order logic. Yeah, we are not going to look at any higher order logic, second order. So our alphabet for the predicate logic consists of meta language as well as a language as usual. So the meta language are the fixed symbols. Oh, perhaps I missed a plus symbol here. Yeah, that should be a plus symbol, meta language plus a language. So meta language consists of the symbols that we will freely use. Yeah, they don't depend on the situation that we are in. And especially I want to point out there exist and equality. Yeah, these two are new additions as well as a countable set of variables. Then we also saw what is a language. It's a predicate language, so it consists of some predicate symbols or relation symbols. Each relation symbol has an arity, and function symbols with some positive arity, and constant symbols. Okay, constant symbols also, they are also like function symbols, but they are zero array function symbols. Okay, so an L structure. So this was the syntax part. This is our alphabet for writing things, but now we have to make sense of them. So on the semantics part, we have an L structure M, which consists of a non-empty set M. Yeah, the curly M will denote the structure, and the the underlying universe is never denoted by curly M. It's always denoted by the corresponding uppercase Roman letter. And for each relation symbol, Rm is a subset of M to the appropriate power. If it is binary, then M square. If it is unary, then M. Then each function symbol is interpreted as a function. Yeah, these are just symbols, they don't mean anything, whereas here it is an actual function of that arity. It takes so many inputs and then it gives out one output. And finally, for a particular constant symbol, you have to choose a fixed element, some element of the underlying structure. Now, right now, still it doesn't have any meaning beyond this. Even if I say the language of the field of real numbers. Yeah, what is the language of the field of real numbers? Tell me. All of you understand the field of real numbers? Yes, what does it consist of? Okay, the structure is this. Yeah? Structure is R, okay, plus, okay, multiplication and 0, okay, 1 and minus. Yeah, we shouldn't forget that. Okay, and on top of it I should write 2, 2, 0, 0, 1. Huh? Multiplicative inverse. Very good question. Is multiplicative inverse an actual function? Why? 0 doesn't have a multiplicative inverse. See, that's a really good question. Please pay attention. I said that you have to take inputs from M or so many inputs from M. Multiplicative inverse, if it takes 0 as input, what should it output? Do you want to formally define 0 inverse is 0 and break mathematics? Yeah, we don't want to do that. So it's not a function. Yeah, multiplicative inverse can be defined using properties, the formulas that we define. Yeah, but right now it's not part of the structure. Now, as you can see on the screen, that mu is a function from j to n plus, because zero array function symbols have a different name. What are they called? Constant symbols. Now I just want to raise a similar question for zero-ary predicate symbols. Yeah, what will be a zero-ary predicate symbol? What will it be? R to the power m, if R is a zero-ary relation symbol, it is a subset of m to the power 0. What is m to the power 0? 1. I mean, it is singleton. So, how many subsets of m to the power 0 are possible? 2. One is empty and the other one is singleton. And empty and singleton are actually other names for false and true. So that is how propositional logic embeds inside first order logic. Okay, so I am just going to write that now. Yeah, I mean, just as a comment here. So propositional logic can be seen as a sub-logic of FOL where the language consists of only zero-ary relation symbols. Okay, so therefore, and yeah, I mean, m to the power 0 is singleton, it is 1. So empty subset of this corresponds to what? False. And 1, sorry, this is true. And true is the name which we give to one subset of this. Now, in particular, it doesn't matter what universe we choose. Even if M1 and M2 are two different non-empty sets, M1 to the power 0 is going to be singleton, M2 to the power 0 is also going to be singleton. So, structures don't really matter. What will be a structure in that case? If your language, predicate language, only consists of zero-ary predicate symbols, what will be an L structure for that? Nothing here, just this. So for all zero-ary relation symbols, you must choose either empty set or 1. So that means it is a valuation. You understand? And an L structure, a structure for such language is simply a valuation. That's all we need to do. So this is like how perfectly propositional logic sits inside predicate logic. Any questions? Okay, let's proceed then. Now, today our job is to look at more syntax and semantics of predicate logic. Yeah, once we start with alphabet, from that alphabet what do we construct? If we are talking about English alphabet, what do we construct? Words. And from words we construct sentences. So there are sentences over here. Yeah, in predicate logic there are sentences, but there are also two different types of words. Yeah, and those two different types are called terms and formulas. Okay, if you remember from my first lecture on logic, yeah, we talked about polynomials. We talked about polynomials, polynomial functions. Yes, so let me recall that bit for now. So polynomial, then polynomial function, then polynomial equation, okay, we can take equations, and then solution sets of polynomial equations or inequalities. These are 4 different kinds and they are very well divided. What is this part called? This vertical first column, what is it called? That corresponds to syntax. Okay, so this is our syntax. And this is our semantics. So here we will, on the other side, we will need the help of a structure. For the first column, we don't need help of any structure. We just need to rely on our language. These are just formal strings of symbols. They don't mean anything. On this side, nothing means anything. On that side, it's about meaning. Now, what is the first row? Polynomials and polynomial functions. If I tell you x square plus y square minus 1, is it true? Does the question make sense? No. I mean something for which the question doesn't make sense, those things are called terms. And I ask you x square plus y square minus 1 is equal to 0. Is it true? Now the question makes sense provided I also give you values for x and y. Yeah, assignments for x and y. So those things are called formulas. So formulas are either true or false. And this is just functions more generally. Okay, terms, which are generalizations of polynomials, are interpreted as functions, actual functions in flesh. And formulas are interpreted as either true or false, depending on the assignment of variables, assignment of elements to variables. Is this part clear right now? And when we are talking about this, what language are we talking about? Everything corresponds to a language. Which language are we talking about here? The language of, come on, polynomials. How do you write x square plus y square minus 1 equal to 0? I mean x square plus y square, x times x, and then plus, language of rings. Okay, so this is all happening inside language of rings. Now what we are going to do is, one by one we are going to define these things. And what should be the ways of defining things? Can you give me? When we don't know anything, what should we start with? Yes, loudly. Recursion, very good. Okay, so first we will define terms and then we will go from there. So L is any predicate language. I am defining L terms and I have several clauses. So TE1, this is a base case, of course. Yeah, TE1, that it says that each variable is a term. TE2, it says that each constant symbol is a term. TE3, it is the inductive clause. First two are base cases, the third one is an inductive clause. If T1 x bar, T2 x bar, blah blah blah, Tn x bar are terms, and f is an n-ary function symbol, then f of T1 x bar, T2 x bar and dot 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 Tn x bar is a term. And TE4, which is the most important clause, what is it? That's it. Yeah, you cannot do anything more. Okay. Now, in order to understand this properly, again think about polynomials. Is x, if x is a variable, is x a polynomial? Is 0 a polynomial? Right. Then is 0 less equal 1 a polynomial? So we cannot use relation symbols over here. And finally, if x is a polynomial, y is a polynomial, then is x plus y a polynomial? Is x times y a polynomial? Is x minus y a polynomial? That's what we are doing here. If x plus y is a polynomial, then x plus y into x minus y is also a polynomial. So we are allowed to apply function symbols in iterative fashion. So in some sense, the function symbols are our basic, they will give you basic symbols, whereas terms will give you more derived symbols, derived function symbols. Okay, so let us look at one example. Yes.
In TE3, like, what additionally have you used T1 like kind of function like in TE3?
Yes, okay, that's a good question. So T1 x bar, what does that mean? So every term will consist of, it may consist of some variables. Now x bar is x1, x2, xk, okay, some set of variables which may or may not occur, but the set of variables that are present in T1 already appear in x1, x2, xk. So we say that x bar is a suitable context for the term T. So perhaps I should write this. Yeah. So say that x bar equal to x1, x2, xk is a context suitable for a term T if the set of variables appearing in T are amongst x1, x2 up to xk. So for example, I can say that x square minus y square is a polynomial in variables x, y and z. It makes sense? When I say it's a polynomial in x, it doesn't always mean that x has to be present. Yeah, it can avoid that. So X bar is a context suitable for a term. Any questions about this now? So here what we are doing, T1, T2 and Tn are n terms which have been already constructed. Now if the set of variables used in them, they are different, then X bar is a context suitable for all of them together. Yeah, I mean there are only finitely many variables being used. So finite union, that's again finite. So therefore X bar is a context suitable for all the terms together, and that becomes a context for f of T1, T2, Tn also. Okay, so let us do an example, it will make things clearer. So for example, just one more thing, the set of terms, the set of L terms is denoted TL. Okay, so far we have used the notation SL in propositional logic, so this is TL. Then for formulas it will be FL, and for sentences it will be again SL. Okay, so let's do an example. What is TL set? L set is the empty language. Yes, so in empty language each variable is a term, each constant symbol is a term. Are there any constant symbols? No. Are there any function symbols? So what are terms? Done. Okay. Then perhaps I should talk about TL ord, the language of orders. What does it consist of? A unique binary relation symbol. Try to be more specific. A unique binary relation symbol. Each variable is a term. Are there any constant symbols? Are there any function symbols? So we are done. Again x1, x2, xk. So unless and until there are function and constant symbols, you can't really do much. What about the language of, let's say, groups? So language of groups, what does it have? Does it have a constant symbol? Yes, so I'm first going to write down all the variables, okay, that's always going to be a part. Then eventually it has one constant symbol, E, okay. Then does there exist any function symbol? The binary operation, yes. So I can apply the binary operation on what? So I can say f of xi xj, yeah, then I can say f of e comma xi. I can also say something like f of xi xj, f of xk e. I can apply it iteratively, correct? And there is also one more symbol which is inverse, yeah, and that I can use also. Did we call it G in the last lecture? Yeah, so then G of x1, G of xi is a symbol, then G of f of xi xj is a symbol, this is also a term, then G of e is a term, and so on and so forth. You can understand, yeah, there is no associativity here. Even if I write iterated things, there is no associativity. There is no commutativity. So f of xi xj and f of xj xi are different terms. So don't use your understanding to simplify terms. Yeah, polynomial in the language of rings, polynomials are written after understanding that the addition is associative, commutative, everything. But polynomials like in L ring, yeah, this is, so if I say x plus, if let's say plus is a symbol, then plus of xy comma z and plus of xy comma z and plus of x comma plus of yz, these are different terms. Yeah, nobody told us that they are the same. Parentheses do matter at this point because we are just manipulating symbols. So technically speaking, yeah, polynomials are not terms unless you write them properly with appropriate parentheses. Right, so you understand this? So as you saw here in this particular example TL odd, that when your language does not consist of any function symbol or constant symbol, then the terms are very simple. So such a language is called purely relational language. A relational language is one which only has relation symbols. Yeah, it doesn't have any function or constant symbols. So purely relational languages, the terms are always the variables. Okay, and this actually tells you that terms should be treated, terms are specific to functions. Constant symbols are also function symbols, zero-ary function symbols. So terms are specific to functions, and hence I am highlighting this part that we are going to interpret them as functions. So right now these are just terms, are just strings of symbols. Now we are going to interpret them as actual functions. But where does that interpretation happen? It must happen in a structure, right? So let us write down these things. Suppose M is an L structure. Okay, and T belongs to TL such that X bar is a suitable context for T. Yeah, what does that mean? We will write T X bar. Okay. Then the value of T in M is a function. Maybe I should say what is x bar, x1, x2, xk. Okay. is a function Tm from m to the power k to m. Recursively defined as follows. Okay, any question in these three lines? We are saying that we are going to interpret a term as a function. Now function must have an arity. Now what arity are we talking about? The number of variables in the context. Understood? Okay, now let's look at this. So this is called V1 because its value. V1 should correspond to TE1. So when we say that each variable is a term, how should we interpret that variable? If T is the variable xi, and I mean of course 1 less equal I less equal k, then Tm from m to the power k to m will take a1, a2, ak and map it to what? Ai. That's the only choice. It's the projection map. Yeah, it always chooses the ith element. Yeah, we are given k tuples, we only choose the ith element. So it is the projection map. Yeah, it is. So Tm is equal to pi I in this case. Okay. Now if I ask you that the term, so I mean this is clear, yeah? If I want to interpret a polynomial as a function, the polynomial is x and the variable set, the context is xyz and I am given values 1, 2, 3, then what will be the value of x? 1. Yeah, out of xyz we only pick the value of x. Yeah, so it's simple. Now if the polynomial happens to be 0, what should be its value at 1, 2, 3? 0. So can you tell me what is V2? If T is C belonging to K, then Tm from m to the power k to m is what? It takes a1, a2, ak, some k tuple, and what should it map it to? C. Not C. C is a symbol. Cm. Cm is an element in our structure. So we simply map it to its interpretation. Okay, so I mean it's a constant function. It's a constant function with value Cm. Yeah, so here I am again writing. So Tm is the constant function with value Cm. I mean if the polynomial is 1, then you will simply map it to 1. No matter what input is given, it's always the same value. Any questions? Okay. Now V3 is a bit more complicated. So look at this T3. So you are given n terms. and you are given f, which is an n-ary function symbol, and then you have constructed a new term recursively. So now we want to understand what is the interpretation of this new term. But because we are using recursion, the earlier functions have already been defined. T1m is defined, T2m is defined, Tnm is defined. And because f is a function symbol associated to f, we also have a function. So therefore, we will apply that function on the previous function. It's a composition of functions. Yeah, that's what our V3 is. So if T is f of T1, T2, Tn for some n-ary function symbol f and terms T1, T2, Tn, then Tm from m to the power k to m is defined as a1, a2, ak mapping to, now pay attention here, it is the evaluation of the function fm at T1 evaluation at a1, a2, ak, then evaluation of T2 at a1, a2, ak, dot 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 evaluation of Tn at a1, a2, ak. So here Tm is a composition. So if we are talking about x plus y, yeah, and my values are 1, 2 and 3, then how do I obtain plus of xy, interpretation of plus of xy? First, I find the value of x, which is 1. Then I find the value of y, which is 2. And then I apply the interpretation of plus on 1 and 2. That's what is written here. It looks complicated, but it's not. Yeah, so for example, yeah, I mean, let's do an example. I'm going to write down the things which you probably understand better. So, add of mult of x comma 0 comma y. Yeah, this is given. You understand this? Add is addition, mult is multiplication, 0 is 0 symbol. In, I can say r plus dot minus 0, 1, okay, in this particular structure. Then I should also give you some more information. No, not the context. Context is clear here. What is a suitable context for this? X comma y. That is a context suitable. But I want you to evaluate at 3 comma 5. Can you do it for me? What is the value? 5. But don't do it in one step. Yeah, logic is about understanding how we are doing it. So I am going to write it on the next screen now. Okay. So add of mult of x comma 0 comma y, and I want to interpret it, this whole thing, at m, in m at 3 comma 5. This is equal to add m, I shouldn't write m, I should write r. Yeah. So this is the interpretation of add in R, then inside I should say mult x comma 0, the interpretation of that in R at 3 comma 5, comma y interpretation in R at 3 comma 5. This is my expression. So this expression I can write as mult R, correct? Then interpretation of x at 3 comma 5, then interpretation of 0 at 3 comma 5, and then add R is what we usually write as plus. Then what is YR? YR is the second projection of x comma y, so that is 5. Then this will be mult R is multiplication, yeah. So XR at 3 comma 5 is 3. So 3 multiplied by, what is 0R at 3 comma 5? 0. Then there is a parenthesis and then 5. So this will be 0 plus 5, which is equal to 5. You do all of that in one go. But when we are studying logic, we have to show our logic. It looks boring. It is boring. I don't deny that. But if we want to understand how our brain works, then we have to go through it. And only if we understand, then we can teach it to a machine. Okay. I'm not going to do any other examples. I mean, I think you got the flavor of what's happening here. Okay. Then perhaps we should move on to the next part, which is formulas. So formulas are generalizations of polynomial equations or polynomial inequalities. Okay, so when I say equation, then I am referring to equality. And equality is what? It is a meta-language symbol, but it is also a binary meta-language symbol. It is a relation symbol. So, if you remember, TE1, TE2, TE3, they were all about variables, constant symbols and function symbols. Formulas are all about relation symbols and equality, and then constructing more complicated formulas from that. Okay, so L formulas. So I am going to say F1 if R is an M-array of relation symbol and T1 x bar, T2 x bar up to Tm x bar are terms. Then R of T1 x bar up to Tm x bar is a formula. I mean, think about it. X is a term, y is a term, less equal of x comma y is a term. X less equal y is a term, correct? Because less equal is a binary relation symbol, so that is a formula, sorry. Less equal of x comma y, I mean that is just way of writing it. We will, in practice we write x less equal y, but when we are treating it as a symbol, less equal of parenthesis x comma y. That is a formula. There is F1 dash. Yeah, why F1 dash? Because we are not talking about any relation symbol from the language, but we are talking about the relation symbol from the meta language. There is only one. Yeah. So if T1 x bar and T2 x bar are terms, then T1 x bar equal to T2 x bar is a formula. I mean, ideally speaking, this should be a subcase of this. But the problem with that approach is that a relation symbol is interpreted as some subset, okay? We don't know which one. It can be empty, it can be everything. Relation symbol, if I go back here, then a relation is simply a subset. Whereas equality should always be interpreted as a specific subset. Equality is always the diagonal relation. It is always the pairs A comma A. So there is no choice involved. That's why we do not want to treat it as a flexible symbol of the language, but a fixed symbol of the meta language. Yeah, so there is no variability. That's why F1 prime is separate from F1. Okay. Then F2. Yeah. If phi x bar and psi x bar are L formulas, then so are negation phi x bar and phi conjunction psi x bar. Any problem about that? X less equal y and z equal to 0. Conjunction z equal to 0. That's the formula. Conjunction of two formulas must be a formula. Negation of a formula must be a formula. As derived symbols, we can also say disjunction, implication, if and only if. Everything just comes under this F2. Okay. Finally, yeah. Now this is the new part. So far we haven't done anything very interesting. So at last we have to talk about quantifiers. So if phi x bar is a formula and phi wj replacing xi is a formula, is an expression obtained by replacing all occurrences of xi in phi x bar by wj, then there exists wj, phi wj replacing xi is an L formula. Okay, I will give you an example. It should be clear. Can you see that x less equal y is a formula? Which clause are we using there? F1. Okay. Z equal to 0 is a formula. Which clause are we using?
F1 dash.
F1 dash. So I put a parenthesis around them. And then I put a conjunction. Is this a formula? Yeah, I mean this is happening in L ring, of course. And now I say that I want to make y a bound variable. So I replace y by w. So what is the expression that I obtain? Well, I will get x less equal w conjunction z equal to 0. Now this is just an expression. Right now this is not a formula. I have to put on top of it, there exists a w. So there is a w such that x is less equal y and z is equal to 0. This is a formula. This is obtained by taking F3, using clause F3. Do you understand what's happening here? Now, here I should point out that W's are called bound variables. W's are bound variables. Why is it a bound variable? Because it is attached to a quantifier. And finally, x, y, z, these are free variables. We will talk more about this in tomorrow's lecture. Yeah? So I just wanted to give you a feel of what formulas are. Oh, wait. I should finish properly. I haven't finished the definition. I should add F4. That's it. And the set of formulas, the set of all L formulas is denoted by FL. Let's stop.